Right, so I'd like to welcome you again. This is an example on power factor correction using a synchronous condenser, right? So it says that an industrial load draws 475 kilowatts at a power factor of 0.8 lagging. Now the plant is extended by connecting a synchronous motor, right, which is a synchronous condenser, in parallel to the load, and the motor is then varied until the overall power factor of the plant is equal to 0.95 lagging. Now if the motor draws 75 kilowatts, calculate the following. Firstly, we need to calculate the power factor of the motor and also the apparent power that is drawn by this particular motor. So we are going to then go ahead and write down the data that is given to us. Right. So let's just reduce this and move it here so we can still see our question. Right. So we are told that we've got an industrial load that draws 475 kilowatts at a power factor of 0.8 lagging. So our first step is to draw our triangle, and we draw the triangle of the load. So you've got your reference, which is the power of my load, and we refer to the power as P1. So let's call this point A and this point B. So obviously I will have a reactive power of my load, and we call it Q1, and this point, let's call it C. And this now shows the apparent power of my load, and I was told that the power factor of the load, theta 1, is equal to 0.8. So let us write our data down for the load. So theta of my load, theta 1, will be equal to the arc cos of 0.8, because the power factor is 0.8. The theory says that for the motor I will draw a straight line starting from the end of the power of the load. So a straight line like that, and this would represent my induction motor true power, right? Then from there I can do a dotted line which is parallel to BC and translate that particular line or power to the bottom here. So this is still your PM, basically ABC. So this is D, let's call this point E. So BD is equal to CE. It's the same line, right? My power factor of my synchronous motor should be positive, so I know that it will have a leading power factor. Let me go ahead and draw that. So this would represent my S of the motor at a positive power factor, theta motor, and obviously at the point, from the point F up to point E, then I have my reactive power of the motor. So with that being said, I can see that from point A to point F, I can draw a straight line which now represents a resultant, a apparent power, SR, which is a resultant of the initial load, which is the white triangle, and the load from the motor, which is the red triangle. So the green triangle there would then be representing my improved power factor or my resultant power factor. So here I would have my theta R given, and obviously PR from point A to D. So I know that PR, which is my resultant power, PR, which is my resultant true power, will be equal to the power from my load plus the power from the motor. Basically, this is equal to AB plus BD. So that represents the total power. Then I do have my SR, which is basically equal to PR cos theta R, like that. And I do have my QR, which is what I need to calculate. So basically, QR will be now the point DF. It's the line D to F. And if I look at this, I can see that my line DF is basically equal to DE minus FE. Right, I'm trying to analyze this so that when we go to the calculations, we just go ahead and take and substitute those particular values. So from the given data, they are telling me that the overall power factor of the plant has been improved to 0.95. So basically that cos theta R is equal to 0.95. That's the power factor of the overall load improvement. Now, theta R is then equal to the arc cos of 0.95. Punch that in your calculator, you will get the angle theta to be equal to 18.195 degrees. Right, so that represents your theta R. So we have tried to represent the whole statement and the given data into our drawing. The next thing is then for us to be able to do the calculations that are required. Right, so to do that, I will just select this. Not erase it, reduce it, so that we can keep it when we look at our calculation. Right, so basically that is our whole statement. We've converted that statement into that. So the next task is to do the first part of the calculation. They say calculate the power factor of the motor. The power factor of the motor is basically given by theta M. We need to be able to calculate theta M. But for us to get to theta M, we have to firstly deal with some calculations on our original load triangle and go ahead and calculate theta M. Right, so our first step would be to calculate the side BC, because we can see that BC is basically equal to DF. So we have to calculate the side BC. And to do that, we are going to use Pythagoras theorem, and we know that our tan of theta 1 will be equal to the side BC over AB. Right? The tan of theta 1 will be equal to BC over AB. The tan of theta 1 in the y triangle is equal to the opposite over the adjacent. That is your tone. Right? So basically BC, which is equal to, on the green triangle, on the red triangle, is equal to DE, is equal to DE. This is then equal to AB multiplied by tan theta 1. AB we are given. Tan theta 1, the angle theta 1, we have calculated that. right? The size of AP, we can see that AP is represented by the true power of the load, which is 475 kilowatts. So this is then equal to 475 kilowatts multiplied by the ton of 36,87, right? So you punch that again in your calculator, you get that this is equal to 356.25 kVAR. So that is the size of our reactive power, which is represented by BC. Our interest is in finding theta M. The question says calculate the power factor of the motor. So now that we know dB, we can be able to go ahead and calculate dF, right? Remember the relationship between DE and FE, and also between DF. So DF would be equal to DE, which is equal to BC minus EF. Right, so that is what we are going to be looking at next, so that we can calculate the size of DF. So we are dealing with the green triangle ADF. If you look at the triangle ADF, we said that PR, which is the true power, is represented by P1, which is the power of the load, plus PM, which is the power of the given load. So therefore, we say in triangle ADF, PR, which is the resultant power, will be equal to the power from the load plus the power from the motor. So these are both given there. We are given 475 kilowatts plus the power from the motor, which is equal to 75 kilowatts, right? So if we add these on our calculator, we land at 550 kilowatts. Right, so this is your resultant power, PR. So your resultant power, PR, is then given by that. Right. So next we want to then be able to calculate the size of DF from the same triangle. I can see that if I apply Pythagoras theorem, I'll say that DF is equal to PR tan theta R. This is equal to 550 kW multiplied by the tan of 18,195 degrees. Right, so if you punch that into our calculator, you will get that this is equal to 180,778 kVAR. So our triangle ADF is now complete. We have the true power, we have the reactive power, and we can get the apparent power basically if we needed it. But our aim is to come and calculate theta M. So to do that, again, I need some space. Copying everything here.
It's not actually here.
Okay, let's reduce. And I'm going to move that there. Right, so we want to calculate FE, and I said that BC, which is on the y triangle BC, is equal to, on my red triangle, DF. Right? Now that we have DF, it means we can be able to calculate FB. So FB is equal to DF minus, so it's DE minus DF. Right? I'm saying FB will be equal to DE, which is equal to BC, minus DF, which we just calculated now there as 180,788 kVA. Right, so then this is equal to, we take the value of DE, which is 356,25 minus 180,778 kVAR, and that gives us 175,473 kVAR. Right, so that means that now we have this distance. Our aim again is to calculate that particular angle. So we have that side and we also have the power of the motor. So because we have those two sides, it means we can basically calculate the angle theta. We know that opposite over adjacent will need the, basically the angle, will give us the angle tan theta. So tan theta m is equal to FE, opposite, divided by the adjacent side, which is basically your CE. CE is this power here, and FE is basically what we calculated in this question, which is 175. So if you put those in numbers, you get the following. This would be 175,473 divided by that given power, which is 75 kilowatts, and this is equal to 2,34. Therefore, the angle theta will be equal to the arctan of 2,34, which is equal to 66,861 degrees. Right, so that is now the angle theta m. The question wants you to calculate the power factor of theta m. This is just the angle theta m, but the power factor of theta m can be calculated by using the following. So we reduce this so we can get some space. Right. Then we say that the power factor, of my motor will be equal to cos theta m. Theta m, I've calculated the 66.86. So the power factor of my motor is equal to the cos of 66.86. And if you punch that again in your calculator, you will land at 0.393, and it's a lagging power factor. No, it can't be a lagging power factor, right? Why can't it be a lagging power factor? We said that the power factor of our synchronous motor is always leading, so it must be a leading power factor. Leading power factor. So for us to solve this question, firstly we have to draw the load, which is the Y triangle. Then we draw the additional motor. Also, then we draw the resultant triangle, and we ended up at that particular answer there. So we look at the second part of the question. And the second part is looking for, they say calculate the apparent power drawn by the motor. Basically, they want you to calculate the value of S, S of the motor. We can use so many different ways, but I can see that the easiest way is just using the Pythagoras theorem, right? Because I see that on my red triangle, S of my motor will be equal to the square root of F E squared plus C E squared, which is then equal to the square root of 175,473 squared plus 75. This is a given value squared. Punch that in your calculator, you get 190,829 kVA, and that was the solution to number 2. Right, thanks for watching. We'll see you guys on the next exercise. On our next video, we'll be looking at dealing with multiple loads. How can we improve a power factor for multiple loads? Right, we'll see you on the next video.